In this video, we'll do an example where we solve a recurrence. So I want to start with the definition of a closed formula, which says that if we have an explicit formula for the terms of the sequence, this is called a closed formula. So a closed formula will not have ellipses or involve other terms. Okay, so let's do an example. The following are all representations of the same sequence, an. Identify the one that is a closed formula. Okay, so in part A, it lists the terms, -5, and then 1, and then 7, and 13, and so on. But there's no specific formula given, and there's also ellipses. So this one's not. So this one's not. I'll put a sad face. Not a closed formula. In part B, it says A0 is -5, so that's indicating one of the terms. And then it's saying AN is an minus 1 plus 6. So that's saying we're adding 6 to the previous term. So this formula involves some of the previous terms. This is an example of what's called a recurrence. But again, it's not a closed formula because a closed formula cannot involve other terms in the sequence. But in part C, I have an equals -5 plus 6n for integers n that are greater than or equal to 0. And that is a closed formula. So this is the one that's a closed formula. So the formula for an needs to just involve the variable n in it. It will not have any of the previous terms. It'll also not be a list like this that has ellipses. Okay, so let's do another example. Suppose we have the recurrence relation an equals 4 times an minus 1. For n greater than or equal to 2, with the given condition that a3 is 48. So in part A, I want to find the first three terms. Okay, so one thing that I want to mention about this, because it says that n is greater than or equal to 2, the smallest value I can plug in for n is 2. And if I were to plug that in, n equals 2, what I get is a2 equals 4 times a1. Okay, well, I don't know what a2 or a1 are. I just know a3. So maybe let's try plugging in n equals 3. So n equals 3, if I plug that in, that'll give me a3 equals 4 times a2. Oh, and I do know a3, so let's plug it in. Plug it in, and I get 48 equals 4 times a2. So I can divide, and I get that a2 equals 12. Nice, so I know one of the terms. I know a2 is 12. In fact, we already know another terms. a3 is 48. Now that I know a2, let's plug it into the other one. So that'll give me 12 equals 4 times a1. And dividing, I get that a1 equals 3. Okay, and at this point, I know the smallest value I could plug in for n was 2, and the smallest a thing that was producing was a1. So my sequence starts at a1. And I know what a1 is now. It's 3. So the first three terms are 3, 12, and 48. Those are my first three terms. Okay. Now in part B, let's actually solve this recurrence relation. And what that means is, for this recurrence relation, I want to find a closed formula. Something like this. an equals some formula that will involve n. No previous terms like this. So, okay. So how can I do that? What I'm given here is that an equals 4 times an minus 1. Let's now use this recurrence again for an minus 1. So I'll keep the 4 that we have outside, and I'm going to replace an minus 1 with the fact that it should equal, like if I plug n minus 1 into my recurrence, that should be equal to 4 times the previous term, an minus 2. Okay, so in other words, if I simplify this, we now have 4 squared times an minus 2. But if I keep going like that, now I got 4 squared times, and I can replace n minus 2 with what I get if I plug n minus 2 into my recurrence. That would be equal to 4 times the previous term, an minus 3. Okay, so this equals This equals 4 cubed times an minus 3. And I could keep going like that, popping up more powers of 4 and keep making this subscript get smaller and smaller. So I can keep going like this. I'll put a dot, dot, dot. And eventually I'll get to the point where I get something, and then I get A1. Because A1, we said, is the first term of the sequence. We saw that in part A. But what's going to be this thing in front? I know it's 4 to some power. And the way I can figure out the power is by noticing a pattern in some of the previous terms. Like if I look at the 3 and this subscript, I notice that 3 added to n minus 3 becomes n. And if I do the same thing with the previous part, 2 added to n minus 2, 2 added to n minus 2, that also equals n. Even back in the first step, I technically had 4 to the 1 here. And if I add that to n minus 1, it becomes n. Okay, so if I keep going like that down to where I am, this subscript and this exponent, so I'll have 4 to some exponent, they need to add up to n. And for that to happen, this exponent will have to be n minus 1. Okay. And, well, I know what A1 is. We got that it's 3 in the last part of the problem. So let's plug in. We got 4 to the n minus 1 times A1 is 3. I'm going to highlight that. A1 we saw was 3, so I'm just plugging in. And now I have my formula. So therefore, we get an equals 4 to the n minus 1 times 3. And that's my closed formula. That is my closed formula for an. Okay, so one key thing that I want to mention about this, which is this is technically not a rigorous proof of why this formula works. If I really want to prove this very formally, we need something called induction. And that's something that we will introduce later in chapter 5. So in this class, we're really just going to scratch the surface on these recurrence relations, because these recurrence relations can get more complicated than they do here. So we are really going to just talk about stuff like this, how to solve it. And we can do that in the method, similar methods to what we did here. Just kind of breaking things down in terms of previous terms and identifying the pattern.